Hello, welcome to Econometrics Melody. In this video, we'll discuss about the F distribution, also called as the Snedecor's F or Fisher-Snedecor's distribution. And let us see some of the useful function. Exponential and logarithm are inverse to each other. That's why we get the value of factorial in the first case and the value of gamma in the second case. And by the help of this example, we want to show that gamma n is equals to n minus 1 factorial, gamma 12 is equals to 11 factorial, gamma 9 is equals to 8 factorial. We cannot calculate the factorial of decimal values while we can calculate the gamma of the decimal value. Now let us see some of the formulae of F distribution, and we will calculate the value of PDF and CDF in our next session. First of all, the value of the mean is equals to degrees of freedom 2 divided by degrees of freedom 2 minus 1, and we want the degrees of freedom to be always greater than 2. Because if it is less than 2, then the mean will be negative, and as the F distribution is the ratio of the chi-square distribution, chi-square itself is the positive distribution. That is why we don't expect the mean to be negative. So is the case with the variance. Variance is equals to twice degrees of freedom square into degrees of freedom 1 plus degrees of freedom 2 minus 2 divided by degrees of freedom 1 into degrees of freedom 2 minus 2 square into degrees of freedom 2 minus 4. And again, we want the degrees of freedom 2 to be greater than 4. If it is less than 4, then the variance will be negative, which is not possible. Here d1 and d2, they represent the degrees of freedom 1 and 2 respectively. Now let us see how do we calculate the PDF. PDF is equals to square root of degrees of freedom 1x d1 into d2 to the power d2 divided by d1x plus d2 to the power d1 plus d2 divided by x, and the complete beta function for the parameters half degrees of freedom 1 and half degrees of freedom 2. So for the parameters a and b, our complete beta function we get when we integrate it from 0 to 1. If we integrate from 0 to any other value, that becomes our incomplete beta function. So 0 to 1, t to the power a minus 1, 1 minus t to the power b minus 1, and we integrate it with respect to t. Complete beta function can be written in terms of the gamma function, or the value of gamma a into gamma b divided by gamma a plus b. Similarly, we get the gamma of z when you integrate from 0 to infinity t to the power z minus 1 et, and we integrate with respect to t. Gamma z can be written as z minus 1 factorial, which we have shown in our earlier example, and this can be further written as z minus 1 into gamma function of z minus 1. So in both the PDF and the CDF, we divide it by the complete beta function, and we have already explained what is the complete beta function. Now let us see how do we calculate the CDF. CDF of the F distribution is the regularized incomplete beta function, and if we divide the incomplete beta function by the complete beta function, then we get the regularized incomplete beta function. So CDF is equals to, up to this point, we get incomplete beta function divided by the complete beta function for these parameters. And for this incomplete beta function, we integrate from 0 and the d1x divided by d1x plus d2 to the power half degrees of freedom 1 minus 1 and 1 minus t to the power half degrees of freedom 2 minus 1. And we integrate it with respect to t, again divide it by the complete beta function. In our next session, we will calculate the value of CDF and PDF by using this generic formula as well. We will calculate the CDF of these three examples. And in order to calculate the CDF, we need to calculate the incomplete beta function, and we need to divide it by the complete beta function. And we will use quadrature class in Mata to calculate the numerical integrals for the incomplete beta function. And we are going to use Stata version 17 for that. And the quadrature class is supported from Stata 16 onwards. First of all, let us set up our function, incomplete beta function, x to the power d1 divided by 2 minus 1 into 1 minus x to the power d2 divided by 2 minus 1, and we integrate it from 0 to this upper value d1x divided by d1x plus d2. So in our first example, the value of d1 is equals to 12 and degrees of freedom 2 is equals to 6, and our x is 1. Now let us calculate the incomplete beta function for this parameter. So we get it as 0.027, and we have placed it over here in our generic formula. CDF is equals to incomplete beta function divided by the complete beta function, and we have the complete beta function over here. So the parameters are half the degrees of freedom 1 and half the degrees of freedom 2, half of 12 6, half of 6 is 3, and 6 plus 3 is 9. And the Stata function f, this will also give us the CDF of the F distribution. Both the generic and Stata functions should give us the same result. It is 46%, nearly 47%. And the FCDF, this is Econometrics Melody written program that will provide the CDF. So 46% O and X is equals to 1, somewhere over here. Now let us see another example, and this time we are going to take the degrees of freedom. Degrees of freedom 1 is 40 and degrees of freedom 2 is 20 for the value of X to be 1.2. Again, we have substituted the parameters and let us calculate it in complete beta function. The value that comes, we have substituted it over here, and we calculate the CDF using the generic as well as the Stata function, and let's see, we should get the same result. It is 66%. So the probability of getting less than or equal to 1.2 for the given parameter is 66%. 66% somewhere over here, and it is 1.2 somewhere over here. Now let us see another example, and the degrees of freedom 1 and 2, they are respectively 8 and 4, and we want to calculate the probability of getting 2 or less than 2. So first of all, let us calculate the incomplete beta function. And when we divide the incomplete beta function by the complete beta function for the respective parameters, we get the regularized incomplete beta function, that is the CDF of our F distribution. And both of them should yield the same result. It is 74%. So the probability of getting 2 or less than 2 for the given parameter, it is 74%. 74% somewhere over here, and it was the value of 2. So we are done with calculating the CDF of the S distribution. Now let us calculate the PDF of the S distribution. Stata function F10, this will help us calculate the PDF of the F distribution. And this is our generic formula, square root of degrees of freedom 1 in d1 x to the power d1 into d2 to the power d2 divided by d1 into x plus d2 to the power d1 plus d2 divided by x, and the complete beta function. Now let us see, both of them should yield the same result. It is 57%. So the probability of getting exactly 0.25 for the respective degrees of freedom, it is 56%, 0.25, 56%, and somewhere over here 56, and it is 0.25. Now let's see another example. Both the Stata and the generic functions should give the same result. It is 58%, and the probability of getting exactly 1, it is 58%. Let us see, what do we get? 58% for 1. So the probability of getting 1, it is 58%, somewhere over here. Now let us see another example when the degrees of freedom are 16 and 10 respectively, and the value of x is 2. So the probability of getting x to be 2, it is 17%, and let us see it by the help of our graph as well. So it is 2 somewhere over here, and it is 16%. Now let us see some more PDF graphs for different degrees of freedom, and this time the degree d1 is equals to 0 and d2 is equals to 10. We get this kind of graph. So when the degrees of freedom is 0, so we don't get any graph. And let us see what happens if we keep the degrees of freedom 2 to be 0. Again, we don't get any kind of PDF graph. Let us keep the degrees of freedom 1 to be 0.1 and degrees of freedom to be 10. So we get this kind of graph. And let us keep both the degrees of freedoms to be decimal points, very small points, and we get this kind of graph. And when the degrees of freedom 1 is 100 and degrees of freedom 2 is 1, we get this kind of F distribution graph. And let us switch the degrees of freedoms, and we get this kind of graph. Now let us see, our degrees of freedom 1 is 2 and degrees of freedom 2 is 10, and we get this kind of graph. And again, degrees of freedom 1 is 10 and degrees of freedom 2 is 50, so we get this kind of graph. Degrees of freedom 1 is 100 and degrees of freedom 2 is 300. We get this kind of graph, nearly a bell shape. Let us further explore, and let us see what kind of weird graph do we get when the degrees of freedom 1 is 600, degrees of freedom 2 is 90. We get this kind of graph. We don't see anything weirdness in this. Now let us increase the degrees of freedom 1, 601. We get some breaking points over here, and degrees of freedom 1 is 600 to 9, degrees of freedom to 90. So the weirdness begins at these points, and let us see whether it will deteriorate if we increase the degrees of freedom 1. This time 603 degrees of freedom 1 and degrees of freedom 2 is 90. And when the degrees of freedom 1 is 604, degrees of freedom to 90, we get this kind of graph. Degrees of freedom 1 is 605, degrees of freedom to 90, we get this kind of graph. And the degrees of freedom 1 is 1022, and degrees of freedom 2 is also 1022. We get this kind of graph. Now let us increase the degrees of freedom 2 and keep the degrees of freedom 1 is 90, and let us see for this large degrees of freedom 2 what kind of graph do we get. We get this sort of graph. So at the peak we see some weird kind of structure, and let us see further if it deteriorates when we increase the degrees of freedom 2. So the F distribution for degrees of freedom 190 and degrees of freedom 2 for this large number, we get this kind of weird graph. And let us see what happens for these values of degrees of freedom 1 and 2. So we get this kind of graph. Now let us compare the F distribution with the normal distribution, and we have written this program, and let us see what happens for these 2 degrees of freedom 6 and 5, degrees of freedom 1, and so we get this kind of graph. At the forefront we have F distribution with this degrees of freedom 1 is 6 and degrees of freedom 2 is 5, while in the background we have a normal distribution with the mean and variance equal to the mean and variance of this distribution. Let us compare once again. When the degrees of freedom 1 is 9 and the degrees of freedom 2 is 7, we get this kind of graph. And now let us repeat the same process when the degrees of freedom, both of the degrees of freedom are equal to 11. Now let us run some simulations and see what happens if we go on increasing the degrees of freedom 1 while keeping the degrees of freedom 2 constant, and we're going to increase the degrees of freedom 1 from 0 to 200 at the gap of 10. Now let us repeat the same process, but this time we're going to increase the degrees of freedom second from 5 to 30, and while we want to change the degrees of freedom 1 from 0 to 200, and it will increase by 10. Now let us see what happens if we increase the degrees of freedom 2 for the constant degrees of freedom 1, and here we are going to increase the degrees of freedom second from 0 to 200, increasing at the rate of 10, and while degrees of freedom 1 is 5. Now let us see for the degrees of freedom 1 30 and degrees of freedom 2, we are going to increase from 0 to 200, that increases at the rate of 10. Now let us see the area graph. This is useful for hypothesis testing, and this is a program written by Econometrics Melody. So this is our F distribution when the degrees of freedom 1 and 2 are 9 each. So our calculated F score is 3.17 at this point, and to the right of it we have 5% of the area, and to the left of it we have 95% of the area. So the calculated score is equal to our tabulated score, or the p-value is equal to our significance level. So in this case we are indifferent. Now let's manipulate the degrees of freedom 1, degrees of freedom 2, and then for the certain F score and for certain our significance level, we want to see what kind of graph we get. Here for this significance level of 5%, our tabulated score is 1.69 over here, and to the right of it, the area is 5%, to the left of it, the area is 95%. And for our calculated score 1.9 somewhere over here. So towards the right of it, the p-value it is 2.27, that is towards the right of it we cover only 2.27% of the area, and to the left of it we cover 97.75% of the area. Now by the graph it is very clear that we were not able to surpass our threshold, or the threshold or the F score set by our significance level of 5%, so that is why we reject the null. So in another word, our p-value is less than the significance level, that is why we reject the null, and we conclude that our F score is actually greater than 1.9. As the F distribution is the ratio of chi-square, and chi-square is generally a right tilt test, so we also perform the right tilt test in case of F distribution as well. Now let us see another example where for the respective degrees of freedom 1 and 2, and we want to test whether our F score, or let us call it X for the time being, X is greater than 1. So for the significance level of 5%, its F score is 1.96. So 1.96 somewhere over here, and towards the right of it we have 5% of the area, and towards the left of it we should have 95% of the area. Now our calculated score is exactly 1. So towards the right of it we are getting 50% of the area, and towards the left of it we are going to get the 50% of the area. Now graphically it is very clear we are able to surpass this threshold set by the significance level, so we fail to reject the null. We have entered into the area of null hypothesis, so that is why we fail to reject the null, and we conclude that F score or X is equals to 1. Now let us see another example where the degrees of freedom 1 and degrees of freedom 2, we have been provided with the degrees of freedom 1 and 2, and our F score is 2 and significance level is 5%. Let us see what kind of graph do we get. We get this kind of graph, and our calculated F score is 2 and our tabulated F score is 1.69 for this significance level of 5%, so 1.69 somewhere over here. And by the graph we are clear that we reject the null. F distribution is generally used to compare the variances, and the null hypothesis is that the variances are equal, and its alternative hypothesis that the variances are not equal. So we conclude that the variances are not equal in this case if the calculated F score were 2. So two-tailed test is very rare in F distribution, but if we have to do it, and it will be something like this. For the degrees of freedom 1 40, degrees of freedom 2 also 40, our F score is 1 and our significance level is 5. Let us see what kind of graph do we get. So this red line, dotted red line, it represents our calculated F ratio. It is 1, and for the significance of level of 5%, so we have a 2.5% area marked by this yellow towards the right, and 2.5% of the area marked towards the left, and at this point 0.53 over here, and 1.87 the upper limit. Now is we are able to surpass this significance level from the both sides. That is why we fail to reject the null in this case, and depending on the situation, our conclusion would be that the variances between the groups or the subgroups are equal. Or in case of regression analysis, we would conclude that the independent variables didn't contribute significantly in explaining the model or explaining the variance of the dependent variable. Now let us survey the process when the degrees of freedom 1 is 50, degrees of freedom 2 is 35, and the F score is 2, and let us see what kind of analysis do we make. So for the significance level of 5%, we see this threshold 0.54 towards the left and 1.89 towards the right, and our calculated F score is 2, which lies just away this threshold. So as we are unable to surpass this threshold from either of the sides, so we reject the null in this case, and we conclude that the variances between the groups are unequal, they are different. Now let us see some of the examples. For the hypothetical data, we are going to run a regression. So we want to focus on the F distribution. The value of F distribution, it is 0.92, and the degrees of freedom 1 is 2, and the degrees of freedom 2 is 297, and our p-value, it is 40%, nearly 40%, and let us depict the same information by our graph. So it is 40%, p-value is 40%, and our significance level is 5%. So the area marked by this yellow color, it's 5%. So we are able to surpass this threshold of 5%, and we enter in the area of null. So we fail to reject the null in this case, and we conclude that the independent variables, they didn't contribute significantly in explaining the variance of dependent variable. So which is further clear if we see the independent variables, none of them are significant. The t-value are less than 2. So the variable income and expenditure are insignificant in explaining the variance of A, and which is reflected in our t-score as well, and we can perform the hypothesis of t-score. We have seen it in our t-test by this area graph, and for the variable income, the t-score is minus 0.64 and the degrees of freedom is 299. And let us see, perform the hypothesis testing. As we are able to surpass this threshold set by the significance level of 5% from either of the sides, so we fail to reject the null in this case. In another word, is the p-value is greater than the significance level, we fail to reject the null. Similarly, for the second variable expenditure, its t-score is 1.2, and let us draw the area graph. Degrees of freedom is 299, and in this case as well, we are unable to reject the null hypothesis for the two-tailed test. And the null hypothesis in this case would be beta is equals to 0 for the respective variable. And for the constant term, we have our t-score significant, which is greater than 2, and let us see whether we get the same value, we get the same result in case of our area graph as well. So for this t-score, minus 11.05 towards the left and plus 11.5 towards the right, we see that we are unable to lie in this region. We are quite away from this threshold marked by this yellow color. That is why we reject the null. Now let us see some of the practical application of F-test besides regression in a one-way ANOVA table. So let us perform the one-way ANOVA. So degrees of freedom 1 is 2, and degrees of freedom 2 is 297, and our F score is 0.67, and we have the p-value 51.50, and let us see it in our area graph. P-value is 51.50, and we get it 51.50. So based on this graph, we are able to surpass the threshold set by this significance level of 5%, and its score 3.02. So in this case, we fail to reject the null. In other words, the p-value is greater than our significance level, so we fail to reject the null. And we have a Bartlett's test for equal variances, and the analysis is made on chi-square. So chi-square, 2 degrees of freedom, we have this chi-score, and the probability p-value is 77.4%. Again, in our chi-square test, we have seen this chi-square area, the area graph, and let us see the p-value, whether we get the same p-value or not. So the p-value is 77.42%, and the significance level of 5% is set in this threshold of the score, chi-score 5.915, somewhere over here. And the chi-square is also a right tilt test, so we are able to surpass this threshold, and we quite entered in the null region, so we fail to reject the null in this case as well. This is also one-way ANOVA, and we should get the same result as the previous one. So the degrees of freedom 1 is 2, and degrees of freedom 2 is 297, and the value of F score is 0.67, which is same as the previous one, and we should get the same inferences in this case as well, and we fail to reject the null, and we conclude that the variances between the groups are equal. And this is also an example of ANOVA, the one-way ANOVA table, and let us see what does it yield. So if we look at it, the degrees of freedom 1, degrees of freedom 2, and the F score is same for the model as well as the age, variable age. So both of them should yield the same result, and let us see, in this case as well, we fail to reject the null, and we conclude the variances are equal. And in the second case as well, we fail to reject the null. Now let us perform the F test in our two-way ANOVA, and we'll cover the ANOVA in detail in some other videos. This time let us see it for an example only, and this is how we can run a two-way ANOVA analysis. For the model, degrees of freedom 1 is 3, and degrees of freedom 2 is 296, and the score F score is 1.92, its p-value is 34.17, and let us see whether we fail to reject the null or we reject the null. So as we are able to surpass this threshold, and we enter in the null region, that is why we fail to reject the null for this score. And for the variable age, we get similar kind of analysis or the result. We fail to reject the null, and for the variable gender, we get similar kind of result. We fail to reject the null. Graphically, it is not clear, but if we compare the p-value with the significance level, it is clear. P-value is quite greater than the significance level. That is why we fail to reject the null. Now let us see some of the important notes and the uses of the F distribution. F distribution, it is the ratio of two chi-square distribution. So if we have a normal distribution represented by Z and its square, it will result in the chi-square distribution. And we get a T distribution if we take the ratio of the standard normal distribution and the square root of the chi-square distribution. And we have already stated that F distribution is the ratio of the scaled independent chi-square distribution, and the square of the T distribution, it will result in the F distribution. Now let us see some of the uses of the F distribution. F distribution is used to test the hypothesis about the variance of two normal population, and it is used in analysis of variance to determine significant difference between variances of two or more groups. It is used in regression analysis to determine the significance of relationship between variables. It is used in assessing the goodness of fit of a model. Similarly, F distribution is used in estimation of confidence intervals for the ratio of two variances. F test statistics is used in multiple regression analysis, quality control analysis, engineering, and financial analysis. F distribution is used in comparing the variances of two or more groups in case control studies or in a sample, in comparing the variance of two or more factors in a randomized block design, and in comparing the variance of two or more groups in a mixed design ANOVA. Similarly, F distribution is used in identifying outliers in a data set, and F distribution is used in other fields where variances are compared. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.